Welcome! Today I'm going to be dealing with the four biggest global warming myths. You know, the ones that keep on coming up over and over and over again. So let's put an end to them once and for all. First, let's all decide what we mean by climate change so we're all on the same page. Global warming is just one type of climate change. It's an increase in the Earth's average temperature over the last 50 to 100 years. It is manifested by many other indicators, such as melting glaciers, loss of sea ice, sea level rise, planting zones moving poleward, stronger storms, and changing migration patterns. Those of us that live locally here in Maryland will notice that the Canada geese no longer migrate to the south in the winter. Most of them just stick around. Well, what are the four most popular myths? The first one, it's the sun. Increases in solar activity are causing the Earth to warm. Now that's possible to happen, but it just isn't happening now. The sun is in fact not warming, it's cooling, and we're going to go into a nuclear ice age, so we don't need to worry about global warming. 3. There's too little carbon dioxide in the atmosphere to make any significant difference. So what are we worrying about carbon dioxide for? And there's the old favorite, which is it's cold outside. So where's the global warming? So let's deal with each of these myths in turn. Well, what does affect the Earth's climate? Well, the sun could get hotter, which in fact it is doing as it evolves along the Hertzsprung-Russell diagram, and it becomes a warmer and warmer star as time goes by. In fact, in about 1 billion years' time, the Earth will probably be uninhabitable because the sun will have got so hot. But that's not affecting global temperatures on timescales of a few hundred years. Changes in the Earth's orbit brought about by shifts caused by the larger planets such as Jupiter and Saturn, and Venus for that matter. We have 3 different types of changes to the Earth's orbit: the eccentricity, the tilt of the Earth's axis, and the precession of the Earth's axis. Each one of these exposes different parts of the Earth to different amounts of radiation over time and can cause warming or cooling. The eccentricity changes on a timescale of about 100,000 years. The precession affects about 20 to 26,000 years, and the tilt every about 41,000 years. These are very long-term changes and don't correspond to the sorts of changes we're seeing in the last 100 years or so. There are other things that affect the Earth's climate. Positions of the continents, which change ocean currents and hence how heat is distributed around the globe. This takes hundreds of millions of years and again is not on the right timescale to explain what we're seeing. Mountain ranges will rise and fall, changing wind patterns and rain patterns. But again, this takes tens of millions of years, and so it's not relevant to the question we're trying to deal with. So let's see what role the sun could play. The red curve here shows global average temperatures averaged over an 11-year period, i.e. a solar cycle. And it shows that over the last 100 or so years, the global temperatures have been going up quite a lot. Below, in blue, shows the sunspot number, which is a measure of solar activity. And you can see that peaked in about 1957 and has been slowly dropping off ever since. The exact wrong trend to explain the increase in global temperatures. So that does not seem a likely mechanism. Well, okay, it may not be sunspots. Perhaps it's flares. Flares produce a lot of energy. Could they be heating the Earth? Well, the biggest flare produces 6 times 10 to the 25th joules, which is an awful lot of energy. The average flare there is smaller than that, though, about 2 times 10 to the 24 joules. Still an awful lot of energy. The Earth receives about 2 times 10 to the 22 joules per day. So a flare can produce 100 times more energy than we receive from the sun in a given day. So it looks like a promising source of energy. But flares emit all that energy isotropically, so it spreads out over space. And the Earth only gets 1 part in 10 to the 17 of a flare's energy because the sun is so far away. And so you can test this by looking at what the effect on the total solar radiance a big flare has. The plot on the right here is a plot of the total solar radiance during a large flare, but it's actually summed over 160 of the largest flares we've ever seen, with the peaks of those flares on 0. And you can see, even with 160 of the largest flares, it makes hardly any difference to the total solar radiance. So again, this is not really a likely source of energy to heat the Earth. The next myth that is being used is we don't need to worry about global warming because the Earth is going to cool down any minute now because we're going into a new grand solar minimum. What is a grand solar minimum? Well, you can see an example of it here called the Maunder minimum, where from 1640 to 1710 the sun produced almost no sunspots, and the energy from the sun was therefore that much lower. So let's assume that the sun is going to go into a grand solar minimum. What will change? Well, first of all, the sun produces 99.99% of the energies that the Earth uses to fuel its temperature and climate. So a change in solar output will in fact change the Earth's temperature. However, it has to be a significantly large amount of change to produce a noticeable change in the temperature. So at solar maximum, the average energy from the sun is measured at 1363.3 watts per meter squared. At solar minimum, it's 1362.0 watts per meter squared. The difference is about 0.04% from the average. Now, that might seem a lot, but remember that's changed over an 11-year period. Orbital variations in the Earth, i.e. over a 1-year period, change the energy received by the Earth by 7%. Now, do you notice each year that change in energy by 7%? Well, you'd have difficulty doing that in the northern hemisphere because the maximum energy we get is in January and the least energy we get is in July. And you notice that January in the northern hemisphere is a lot colder than July. So that makes very, very little change in our overall temperature. In fact, that's much more influenced by the angle of the sun due to the seasons. But let's go back to this figure again. And often the Maunder minimum seems to be associated with very cold weather in Western Europe, like frost flares on the Thames River, as illustrated in this painting. But the Little Ice Age stretched from 1350 to 1850. So the Maunder minimum occurred during the Little Ice Age, was not at the beginning of the Little Ice Age. It didn't cause the Little Ice Age. And in fact, the coldest temperature in the Little Ice Age occurred about 50 years before the Maunder minimum. The other thing is that these ice flares didn't occur all during the Maunder minimum. Only a handful of the 50 or 60 of these ice flares that have been recorded occurred during the Maunder minimum. So again, it doesn't seem to be associated with solar activity. There just was a long period of cold weather in Western Europe, and the Maunder minimum happened to occur during that period. Well, another thing that changes the temperature of the Earth is the Earth's atmosphere, at least its composition. The Earth's atmosphere is made up of 78% nitrogen, 21% oxygen, just less than 1% of argon, and then some trace gases. And if you look at the trace gases, the primary trace gases are carbon dioxide, neon, helium, methane, nitrous oxide, and ozone. Oxygen, nitrogen, and argon are not greenhouse gases, so they have no effect on our temperatures, nor are helium or neon. So we're really dealing with just these 4 trace gases: methane, nitrous oxide, ozone, and primarily carbon dioxide. But we've missed out one major greenhouse gas here, which is often omitted from the conversation and shouldn't be, and that's water vapor. There's about 2% water vapor on average, and that can make up something like 60% of the warming that we see. And so we should pay a deal of attention to the amount of water vapor in the air. So let's take a look at that. As I said, water vapor is a powerful greenhouse gas. It's very short-lived in the atmosphere, from hours to days at most, So that makes its effect that much less. It has no effect at high altitudes. Why is that? Because as you go up in altitude, the temperature drops. As soon as the temperature drops below the freezing point of water, things called clouds form, little ice crystals form, and they no longer have a greenhouse effect. So the higher you go, less and less water in the atmosphere, so less and less greenhouse effect from it. And so it's mostly effective near the ground, but as you go up, the amount of effect it has is almost zero. And it's the other greenhouse gases that we mentioned before, primarily carbon dioxide, that are the main determinants of the heating of the Earth. Well, how hot should the Earth be? Earth temperature at this distance from the Sun should be about minus 20 degrees centigrade. This was first measured by Fourier in about 1650 or so. The measured average temperature is about 16 degrees centigrade. So we're 36 degrees centigrade warmer than we ought to be. And this effectively is the discovery of the greenhouse effect. We can look at our nearest companion, the Moon, which has no atmosphere and is about the same distance from the Sun as the Earth is, and its average temperature is about minus 10 degrees centigrade. So you could actually see the effect of greenhouse gases in the atmosphere comparing the Earth's temperature to the Moon's temperature. So what is exactly the greenhouse effect? Radiation from the Sun passes through the Earth's atmosphere uninhibited apart from the effect of clouds and heats the ground. The ground re-radiates that temperature in the infrared. Now the infrared can pass through most of the Earth's atmosphere, particularly the oxygen, nitrogen, etc., without any problem, so can escape. However, there are the greenhouse gases in the atmosphere, water vapor, carbon dioxide, methane, and so on, near the surface that make it bounce around, so it has a very tortuous path to escape. So it's rather like a blanket, keeps us warmer. As you go higher in the atmosphere, water vapor plays a lower role, and so it's really the carbon dioxide, methane, etc. that are the governing elements. They absorb the outgoing infrared radiation and reflect a lot of it back towards the Earth. So it's an extra source of heat coming back into the Earth. And that's where the temperatures rise. Well, how much carbon dioxide is too little? Let's try this little thought experiment that I've shown before. Consider an empty tube with nothing in it at all, and we shine some IR photons in one end. Say we shine 100 IR photons in the other end. How many will we get at the other end? If there's nothing in the tube, we'll get 100 IR photons at the other end. So now we're going to fill that tube with nitrogen gas, and we found that nitrogen gas doesn't affect infrared radiation. So if you shine 100 photons into this tube full of nitrogen gas, you'll get another 100 photons out the end without any interference from the nitrogen. Now we know that carbon dioxide is a greenhouse gas, as we're going to fill the tube with just enough carbon dioxide to absorb half the IR photons. So we'll get 50 IR photons at the other end. So what do you think will happen if we fill the tube with the same amount of nitrogen and the same amount of carbon dioxide and shine 100 photons into the tube? Now here we have the 100 IR photons going in one end, and the nitrogen will have no effect on it, but the carbon dioxide will have the same effect as it had before, so there'll be still 50 IR photons coming out the other end. So this, the third example here, is 100% carbon dioxide atmosphere. The fourth example here is a 50% carbon dioxide atmosphere, yet the effect is between the two is the same. So the percentage of carbon dioxide in the atmosphere does not matter. It's the absolute amount of carbon dioxide in the atmosphere that matters, and that's called the partial pressure. We've all heard the complaints. Oh, it's bitterly cold here. Where is global warming to help us now? We've just had this terrible weather in Texas, for example. Texas is a southern state, and you don't really expect to get harsh winters there. Yet here up in Maryland, where you expect to get 15 to 20 inches of snow a year, we've hardly had any. So what's going on? Your local weather is not an indicator of global climate trends. In fact, it's not even an indicator of national climate trends. Here is the picture for December, and you can see In December, the southern states, including Texas, had extremely warm weather all the way up also along the east coast into the northeast. Yet the central northern states and the west had colder than average temperatures. So if you're living in the southern states or in Maine, for example, you'd think, oh, this is a lovely winter. We don't have any problems at all. Whereas if you were living in Washington or Oregon or North or South Dakota, Montana, you're thinking this is an awfully cold winter. So your local weather is not really an indicator of what's going on around the world. Let's take a look at the global temperatures for December as well. This is what's called a percentiles map and shows where there's record warmth, that's the deep red, compared with record cold, that's the deep blue. You'll notice there's a lot of record warm areas, particularly Europe, the Polynesian Islands, and so on. There's not very many places that are cold. In fact, the main cold area is off the western coast of South America, and that's the evidence of La Nina, which is currently prevalent. And that's a cooling effect. So global temperatures are actually being dragged down by this La Nina. If this changes to El Nino like it's likely to do later this year, global temperatures are going to soar. So what conclusions can we draw from all of this? Well, first of all, the sun is not causing global warming. The sun is not going into a grand solar minimum and will cause a little ice age. There is plenty enough CO2 in the atmosphere to cause the observed warming that we're seeing. And your daily weather observations are a poor indicator of total climate trends measured over decades. So thank you for watching. Until next time, stay safe and goodbye.